welcome.
Good evening, class. I hope everybody's doing fine. We are looking at section 6.2, trigonometric functions, and the approach we're going to use is the unit circle. First, let's quickly recap what we've done. So we looked at the first section, and in the first section, we dealt with a lot of basics, okay, angles, the measures, some definitions, vertex, line, ray, initial side, terminal side, and so on and so forth. A couple of important formulas we used. One of them was the relationship between degrees and radians. As you can see, d over 180 is r over pi. That's a very important formula to remember. Knowing the initial side and the terminal side when we are dealing with an angle, okay, in standard position. Initial side is along the positive side of the x-axis. 1 degree is 60 minutes, 1 minute is 60 seconds, and therefore 1 degree is 3600 seconds, something that we know just like we do with, clocks. We know velocity is defined as total distance over total time. So along a curve, V becomes S over T, where S is considered the length of the arc. And then omega is called the angular velocity, okay? And that is theta over T, and it works out the relationship between the two is such that V becomes R omega. Bear in mind that S, the arc length is R theta, and the area of a sector is simply put is A equals 1/2 R squared theta. In both cases, as I mentioned, you can use a circle and compare the area to the area of a circle, pi R squared, and for the arc length, compare it to the circumference, C equals 2 pi r, and you should have no problem seeing what's going on. So having said that, let's go over what's happening in the next section. All right, so let's put this slide mode. As far as definition is concerned, everybody remembers the general formula for a circle which is centered at origin is x squared plus y squared equals r squared. If the radius is 1, then we call it a unit circle, in which case the formula becomes x squared plus y squared equals 1. And so as we look at this case, okay, S or T, okay, that is really the arc along the circle, in this case, the circle of radius 1 or the unit circle centered at 0, 0. So we define T to be a real number, and we let any point on the circle be represented obviously with the coordinates x and y, okay? And now that we have that, and this is important now we are going to define sine and cosine accordingly, okay? Which means we are going to define sine t as the y coordinate, cosine t as the x coordinate. Now, the rest of the definitions, actually, most of you remember the relationship between sine, cosine, and the rest of the trigonometric functions. So you can figure the rest of them out as long as you know those two. For example, everybody remembers tangent is sine over cosine, okay? Or if you're dealing with a right triangle, is the opposite over the adjacent, and it becomes y over x. So as long as you have those three, the rest of them are the reciprocals. Now we will go over the reciprocal identity, but that should be really helpful. So what I want you to remember, if you look at the very top, x squared plus y squared equals 1. A point on a circle of radius 1 centered at 0, 0. The circle is called the unit circle. Okay. X and y represent cosine and sine. X is cosine and y is sine. As long as we remember that, then we can get the rest of it. So again, any pair has coordinates x and y. The first coordinate x represents cosine and the second coordinate represents y. So with that being the case, let's look at a very simple example to see how this thing works. We want to find the exact values of all trig functions, okay, when a pair is given. So first, we put that, we locate it, we plot that, okay, and it ends up being obviously on a unit circle. Negative 1/2, square root of 3 halves, that gives us the second quadrant. So it's important to understand that. And so x represents cosine, okay? And so x must be negative 1/2. Therefore, cosine is negative 1/2. Y is represented by sine, so sine must be square root of 3 halves. So as long as we have those two, the rest are very simple, okay? Now, tangent is y over x, or if you don't want to remember it in that fashion, you remember that, I hope you remember that tangent is sine over cosine, okay? And as long as we have those three, then the reciprocals are the rest of them, meaning cotangent is 1 over tangent, cosecant 1 over sine, secant 1 over cosine. So as long as we can recognize these two, the rest should come very easy. By the way, again, we have no problem with the complex fraction. I'm just showing you the answer for the rest of them. Simply put, we are using, we can say definitions, or we are using the reciprocal identities. Okay, the reciprocal identities. Sounds good? Everybody is okay with that? We're going to move on, class.
All good.
Excellent. We want to find the exact values of the trig functions of quadrantal angles. Quadrantal angles refer to the angles, on x-axis, the y-axis, and as long as we remember something very simple, okay, and that is x and y. X is cosine, y is sine. So just for the sake of argument, as you look at the first one, you see the angle is 0. So I hope you see that means cosine 0 is 1. Okay, cosine 0 is 1. So let's just this is cosine. The angle is 0. And this is sine. So quadrantal angles, just remember the coordinates and you can figure out what they are, okay? When we know cosine and sine, we can figure out the rest of it. Now, tangent a sine over cosine becomes 0. The other three, just the reciprocals, just the reciprocals. I hope you remember this from trigonometry, and if you don't, I hope the unit circle and the fact that x is cosine, y is sine will help you figure it out. For the sake of argument, if you are looking at part B, okay, theta equals pi over 2, that means we are looking at this circle, right? So let's give everybody a quick moment. See if you can figure out all trigonometric functions. Okay, so let's quickly pause this for a moment. So cosine of pi over 2 or 90 degrees is the x coordinate is 0, and sine of pi over 2 or 90 degrees is the y coordinate is 1. You can quickly figure out the rest of them, I hope. Does that make sense, everybody?
Yes.
What about 180 degrees or pi? Theta or is equal to pi or 180 degrees. The coordinates are negative 1 comma 0. X represents cosine, so cosine of pi must be negative 1. Sine of pi must be 0, and the rest become nice and easy. The last one we want to look at is 3 pi over 2, which is the same as 270 degrees. So we look at the coordinate. The coordinates are 0, comma, negative 1. Okay. So the x coordinate represents the cosine. So cosine must be 0. Y represents sine. Sine must be negative 1. Okay. And we can write the rest of them accordingly. Tangent is sine over cosine, becomes negative 1 over 0, which is UD stands for undefined. Undefined. All right. We're going to move on. Again, really there is no need to memorize this. Understand the location of a specific value, as I mentioned. For example, when you're looking at 180 degrees or pi, you should recognize the location of your point, which is negative 1, 0. You can figure out the whole thing. This definition, in essence, is being repeated, sine theta or sine t. So I don't want to, dwell on this and spend too much time on that. Theta represents an angle and t represents an arc, and they correspond to each other as far as the bottom table is concerned. It's just giving us what we just went over, okay? Common arcs like 0, 90 degrees, 180 degrees, 270 degrees. We just covered that in the previous page. You can come back if you have to memorize it. I wouldn't memorize it. I would just try to remember the location based on a unit circle, and immediately we can figure out goes on. All right. So we want to the exact value of trig functions that are multiples of quadrantal angles because we know what they are. All we have to do recognize the location. Okay. Example, sine 3 pi. Okay. Everybody knows pi radians is a complete revolution, which means we are going to go half a revolution more, and it gives us the same location as pi. In fact, some of you may remember that sinusoidal functions are periodic functions, and their period for a basic sine and cosine is 2 pi. So if you subtract 2 pi from pi, that's another way of doing that. Then this becomes the same as sine of pi. Okay, kind of look at that, you know, I guess it's fairly straightforward. You would remember that. And so because looking at sine, that means the y coordinate and therefore is 0. Okay, now let's look at the next one, cosine of negative 270 degrees. Let's give everybody a moment to figure this out. Okay, so let's see what we get. When we say negative 270 degrees, that means we're going to go clockwise. Which puts us in the same location as pi, positive pi over 2. In other words, negative 270 degrees and positive 90 degrees are coterminal, which means they have the same value. Okay, so again, we are looking at the fact that it's x or y. Okay, class? X or y, and accordingly, we come up with the answer. All right. We are ready for the next one. Fairly straightforward. We want to find the exact values of trigonometric functions for pi over 4, which is the same as 45 degrees. And of course, we can use the information we have regarding the unit circle. As you can see, the point lies on the line y equals x, because it's 45 degrees. It's the same as the line y over x, y equals x. And so if we want to go with that, we know that x squared plus y squared equals 1. So let's replace the y with x as well. Now it's a simple case of solving for x. We have 2x squared equals 1. X squared equals 1/2. X is plus minus 1 over square root of 2. And we keep the positive one only because P is located in the first quadrant. Okay, it's important to know that really you have two answers. Okay, if you think about this, x squared equals 1/2 and x is plus minus. Whether you write 1 over square root of 2 over 2 is fine. Normally we rationalize it, but that's not really the point here. But we keep the positive only. Okay, so if y is square root of over 2, so is x. So x and y, x represents the cosine, Y represents the sine. Both of them are square root of 2 over square root of 2. Square root of 2 over 2. Both are the same. Now, just for the sake of argument, I hope you see that tangent is what? Sine over sine. They are identical. Tangent becomes 1. Okay? So tan. Okay. Let's say over here, I'm going to use power 4. What is that? Sine over cosine. That's 1. The rest of them are the reciprocals. So we get this shape and we get these answers. Does that make sense? Is everybody okay with that? So so what we are doing, we're going to look at some common arcs. Besides the quadrantal angles, we are looking at 45 degrees or pi over 4. That is also a common arc. We should be fairly comfortable with that. Again, this is something you should know. You should know sine and cosine of pi over 4 is square root of 2 over 2. Tangent is 1. The rest are simply the reciprocal. Okay? All right. We're going to move on, class. All right. We want to find the exact value, starting with this case. Sine of 45 times tangent of 45, knowing that each one has a specific value. For example, sine of 45 is, actually stop this here for a second. Give me 1 second. All right, so you know sine is square root of 2 over 2, tangent is 1, their product is simply square root of 2 times 1, which is the same thing. Secant of pi over 4, cotangent of pi over 4. We want to look at their product, okay? And again, in case you don't know it, you know secant is 1 over cosine. So it ends up being square root of 2 times 1, which is simply square root of 2. Now, these three, I'm going to give everybody a minute to figure all of them out. This is a simple case, and they're all common arcs. Sine of 45 degrees, cosine of 180 degrees. Sine is 2 over 2, and cosine of 180 is negative 1. Okay, hopefully everybody remembers that. Okay. Tan of pi over 4 is positive 1 minus. Sine of pi over 2 is negative 1. The result is 2. Secant of pi over 4 is square 2 quantity squared, so it becomes 2, and 1 becomes positive 3. Okay, class? Sounds good?
Got it.
Yeah.
Perfect. So we're going to move on. Don't forget, this is our pi over 4 class, okay? All right, what we do now we want to look at a couple of special cases, okay? And what about 30 degrees and 60 degrees? And to complete the answer, we are going to approach it in the following manner, okay? We are going to add, okay, we gotta draw that, and the way we are going to handle it, make the hypotenuse to be 1. We make the hypotenuse to be 1. And so all we have to do, one more triangle and there. So now, as you can see, if the hypotenuse was 1, so is the rest of this, all of them are 1. What are we with? We are dealing with a triangle which has, because every angle is now 60 degrees, right? Everybody remember equilateral. All sides are equal to 1. Sides are equal to 1. And being the case, A must be half of that. And B can calculate it using Pythagorean theorem. A squared plus B squared equals C squared. And we end up with B side being square root of 3 over 2. Square root of 3 over 2. Now we're going to use this to find the trigonometric functions for both cases. So, before we move on, is everybody clear so far? So all we did, we started with a right triangle, having the hypotenuse equal to 1. We put an identical triangle to one side, we added. It resulted in an equilateral triangle having all sides equal, all angles equal. Angles are 60 degrees, and the sides are 1, which means now that we have the sides A equals 1/2 and B equals square root of 3/2, take a look at this one. So if you happen to have a 60 degree or pi over 3 angle, okay, and the circle is a unit circle, right class? The unit circle. So that simply means what? It means the x coordinate is 1/2 and the y coordinate is square root of 3/2. All right, so we are ready to actually calculate just about everything here. So what do we have? First and foremost, sine of pi over 3 is the y coordinate, which is square root of 3 over 2. And cosine of pi over 3 or 60 degrees is the x coordinate, which is 1/2. As long as we have those, we can figure out the rest. So we have those. We can figure out the rest, class. That shouldn't be a problem. Does that make sense? Is everybody okay with this? All
Yes.
right. So I can't emphasize the importance of remembering which one represents um, sine, which one represents cosine, okay? As long as we remember that, it works out nice and easy. So now tangent. What is tangent? We can calculate it as sine over cosine, and cotangent is the reciprocal of that, 1 over square root of 3, or square root of 3 over 3. We're going to do the same thing, same process, to find the exact values of trigonometric functions for the other one, 30 degrees or pi over 6. 30 degrees or pi over 6. Can everybody hear me, class?
Yes, but I think you're like lagging a little bit and cutting sometimes. Like your microphone's cutting. I don't know.
I see. Okay, actually, that's why I try to speak slowly, so I try not to speed up. But please, by all means, stop me and let me know, okay, class? Because if in case you have a hard time hearing me, uh, I have no idea, so let me know and I slow down.
Okay. Thank
In
you.
fact, my pleasure. In fact, any questions before we move on? Everybody okay with this stuff? Perfect. All right. So now we're going to do the same thing for 30 degrees. So we put it up. So it's a very simple process. Everybody can figure this out in no time. So we are going to pause the recording, let everybody work on it for the next minute. So it's very straightforward. Sine is 1/2, cosine is square root of 3/2, and you can figure out cosecant and secant are the reciprocals, and tangent is sine over cosine. Cotangent flips over. So those are the values. And again, we really should know them. At the very least, the first three, sine, cosine, and tangent, we can figure out the rest. So just a quick recap. The common arcs we have covered so far are the quadrantal angles of 0, 90 degrees, 180 degrees, 270 degrees. And when we come back to 360 degrees or 2 pi is the same thing. We also covered 30 and 60 and 45 degrees. We need to know them. Those are considered common arcs. And also we should know multiples of them. And that is fairly easy. All you have to do, use the same values, pay attention to the quadrant, whether it becomes positive or negative. So here's an interesting application we are going to look at. Could somebody be kind enough to read the question, please?
A rain gutter is to be constructed of aluminum sheets 12 inches wide. After marking off a length of 4 inches from each edge, this length is bent up at an angle theta. See figure 27 below. The area A of the opening may be expressed as a function of theta as area. Is that A for area or just
A of theta.
A of theta equals 16 sine theta times cos theta plus 1. Find the area A of the opening for theta when it's 30 degrees, theta when it's 45 degrees, and theta when it's 60 degrees.
Thank you so much, class. Okay. Um, First, let's justify why this is the case. As far as evaluation, you just plug in, it's not a big deal. For example, for 30 degrees, you know sine is 1/2, cosine is square root of 3/2. Okay, so it can be easily calculated. But let's look at the proof. Okay, as you look at the shape, you notice it's a trapezoid. So the area is half of the height times base 1 plus base 2. That's the first thing I want you to notice. This is the formula we use, okay? I'm going to discuss each piece, okay? So we are looking at the height, okay? Be 1/2, okay, times the height, which is 4 sine theta, okay? Take a look at this, class. The height is b, and it's equal to 4 sine theta, because if you look at this, small triangular shape, this is 90 degrees. Okay. So sine theta is the opposite. The opposite. B over the hypotenuse 4. And so B is 4 sine theta, which we are calling it h, the height of the trapezoid. So that's how we arrive at it. Now, there's different colors. This one in yellow is 4 inches. That's one side. Let's say B1. Dashed blue line is B sub 2, and it has 3 pieces. As you can see, where it reads 4 cosine theta. Okay, let me use also a different color for each piece. This piece in green is 4 cosine theta, and it's the same as the other piece on the right side, and the one in the middle is 4. So that's why I want you to see that B sub 2 becomes 4, the middle piece, plus 4 cosine theta, plus 4 cosine theta. So it simplifies. It simplifies if you multiply 1/2 and 4, you get 2, and you take the 4 out, it's, oh boy, give me 1 second. Let me write that for you. It ends up being 16. I'll put it up here. Okay. Well, you do have it here, right? So if you simplify, okay, if you simplify, you have this step. A is 16 sine theta times cosine theta plus 1. So for 30, 45, and 60, you simply plug in. That's all there is to it, class, okay? Now, I didn't put it in a proper order, sadly, but I guess everybody's okay with that. So now, if you plug in 30 degrees, the values that you have, you can come up with 4 squared root of 2 plus 8 precisely. You use a bunch of decimals to get with 14.93. I don't want to waste time on the other 2 class. You just plug in 45, plug in 60, you evaluate it. So I'm going to show you the answer. But the part that I meant to show you was this part in blue. The main part, class, is the proof. I'm interested in the proof, okay? And it just plugging in 30 degrees or 45 degrees or 60 degrees shouldn't be a big deal. Okay, sounds good, everybody?
Yes.
Yes.
All right, again, everybody heard me because I want to quickly recap on this, and that is the following. I was interested in showing that the area which is in the shape of a trapezoid, we can prove it to be 16 sine theta times cosine theta plus 1. That's what I was trying to show. Okay, class? Now the rest is just plugging in and remembering common arcs and their trigonometric functions. That's all.
So just to confirm, is that always the area of a trapezoid?
Yeah, that looks like a trapezoid. Do you see that?
Yeah, but half of h times b.
Yeah, half
b1.
of h times b1 plus b sub 2.
Oh,
Half
okay.
of the height, b sub 1 and b sub 2 are considered the bases. There are two different bases.
That's a big takeaway. Thank you.
Yeah, sure. B1 and B2. Sometimes they use lowercase b plus uppercase b. It's just two different bases. They don't have the same, uh, size. That is actually the definition of a trapezoid, okay? It's a four-sided figure where two sides are parallel, okay? So here's the next topic I want to mention. So those are we have discussed them. You have to remember. The thing I want to add is this. Again, there are two ways to remember uh, integer multiples of those. One is if you do drawing as it happens here, that should help. The other one is all you have to do, remember the same values in the first quadrant, okay? In the other quadrant, okay, remember that what happens to x, what happens to y. Remember, x represents cosine. So if x represents cosine, then in the second quadrant, okay, x becomes negative. Do you see that? Well, if you look at this one, just look at this one and see what happens. Okay, so now you should see what's happening here. Okay, so if pi over 3, cosine of pi over 3, okay, just, so if cosine of pi over 3 is 1/2, then right away cosine of 2 pi over 3 has the same value. All you have to do, figure out the sign. In the second quadrant, it becomes negative. And the same thing, happens for the rest of them. You should really know. As long as you know that, it's really not a big deal then. Figuring out what you are going to get. Sounds good? Everybody okay with that, class? Okay. So I wouldn't worry about that too much because you should figure that there are other ways, okay, that, for example, the reference arc, but understand the multiple integers, they have the same numerical value. It is the sign that changes. I hope that makes sense to everybody. All right. For example, if you're looking at finding cosine of 150, okay, there are a couple of ways to approach that. You can do the drawing, okay, as it was in the previous page, okay, and you figure it out, okay. Or what I like to mention, okay, this is, let's write the first one down, okay. So this is from the graph, as you can see, okay. The thing I want to add is the reference angle. How many people remember that? or sometimes they call it reference arc. Reference arc refers to the angle that the terminal side makes with the x-axis. What do we mean by that? So if we look at 150 degrees, first I hope everybody recognizes that 150 degrees, okay, puts us in the second quadrant, because 180 degrees is the, what do you call it? 180 degrees, or pi, is the straight angle, right? So when you're looking at that one, all you have to do, notice that this one has a reference arc and the notation is theta sub r or theta prime or theta hat. I'm showing you different notations because it really depends on which text you're using. For 150, the reference arc is 180 minus 150, which is 30 degrees. Which means the answer is the same as cosine of 30 degrees. However, cosine is negative in this second quadrant. Okay, everybody? That sounds good? Is everybody okay with that? Now,
Yes.
sine of negative 30 degrees is the same as sine of 30 degrees. But you have to figure out where it ends. In other words, the quadrant. Okay? Which quadrant is that? That one is in the fourth quadrant. Sine is the y coordinate, so it becomes negative. Okay? Now, tan of 4 pi over 3, of course, you do have it right then and there. If you look at the graph, it's just sine over cosine. Okay. Or here's what I want you to see as far as the reference arc is concerned. The reference arc for this one, class, is this much. Okay, let me make sure everybody understands why. Okay, let me use a different color because it may be hard to see because we do have a green one here. Give me 1 second. So for 4 pi over 3, this is the reference arc. Okay? Because it's in the third quadrant. And so that means because it's larger than 180, and by the way, you always compare the closest, x-axis. So 4 pi over 3. So reference arc would be 4 pi over 3 minus pi. Pi is 3 pi over 3, and it makes you pi over 3. It makes it pi over 3. Now, what is tan of pi over 3? It's square root of 3. Now, as far as the quadrant is concerned, tangent in the first quadrant and in the third quadrant is positive. Why is that? Because tangent is the ratio of sine and cosine. Sine and cosine are both positive in the first quadrant and both negative in the third quadrant. Okay. Now, sine of 7 pi over 6, we want to discuss that. You see where we end up. Okay, if you're looking at sine of 7 pi over 6, which quadrant is that, class? Can anybody tell me? Sine of 7 pi over 6. Class 6 pi over 6 is pi, so it gives us the third quadrant, right? So it's the same as pi over 6. Sine of pi over 6, all you have to figure out if it's positive or negative. So it's the same as sine of pi over 6. In the third quadrant, sine is negative.
Professor, you're cutting a little bit.
Okay. What is the reference arc for 7 pi over 6? It's because it's larger than pi and it's in the third quadrant, you subtract pi. So it's the same as pi over 6. Sine of pi over 6 is 1/2. However, you should pay attention to the quadrant. You can figure it out. I hope this is helpful, class. Okay. Understanding either way, going by doing the drawing and figuring it out, or by the reference arc. You really have to get comfortable with the reference arc, and it makes life easier. Okay, class? All right. Let's finish the section quickly, and then we take a few minutes of break. Approximation. I assume everybody can approximate, okay? All you have to do, use a calculator. Now, because this is in degrees, you put it in degree mode. If the last one is pi over 12, you put it in radian mode. So the first one, cosine of 48, make sure it's in degree mode. That's the only thing that is important, degree mode. And you can come up with the answer. So what about cosecant? Come up with sine. And the reciprocal is the answer. So 1 sine of 21. What about tangent? Make sure you put that in a radian mode. I really can't emphasize this enough. Okay, class? Sounds good? I want to go over the last topic of the section, class. Before I do that, is everybody okay with this? Is there any questions? So using a calculator, the only thing you want to be careful, it's the mode, okay? It's in degrees or it's in radians. And if you want, I can show you on a calculator, but in any event, let's finish that. And if you need it, I'll bring it up maybe when we start the next section so you can see that. All right, here's the next topic. What if we don't have a unit circle? Rather, we have a general case where the center is still at 0, 0, and x squared plus y squared, instead of being 1, is r squared. Okay, so that works in a similar fashion. And so in this case, definitions are as follows. In fact, this is the general definition for the unit circle also. But as an example, if you look at this one, class, I just want to make a point. This is the same definition we saw with respect to the unit circle. Y equals R. But what was R? R was 1. So we said Y. So this is general form, not a big deal, okay? And so instead of saying Y represents the sign, it's Y over R that represents the sign. Instead of saying X represents cosine, it is X over R that represents cosine. And why is that? Because we are no longer dealing with a unit circle, okay? So the unit circle has given its spot to a general circle of located at 0, 0 with a radius which is different than 1. So let's quickly look at the last question of the section. It shouldn't take more than a couple of minutes before we take a break. So we want to find the exact values of the 6 trigonometric functions for this case. So the very first thing you need to know is to plot the pair. Now, before we plot it, can anybody tell me which quadrant it ends up being? 4, comma, -3. First, second, third, or fourth quadrant?
Fourth quadrant.
Fourth quadrant. Everybody agrees with that? Now, the other thing is that you have to know x is 4, y is -3, and you have to calculate the r, yes? Using Pythagorean theorem. Now, in the fourth quadrant, okay? In the fourth quadrant, x is positive. Everybody knows that, right? If x is positive, so is cosine. If cosine is positive, the reciprocal of that 1 over cosine, which means secant is positive. So the very first thing, we calculate the r, giving us this situation. So the r is 4 squared plus -3 quantity squared. 16 and 9 give us 25, comes out as 5. So what is cosine, what is sine is very straightforward. Y over r or b over r, it depends on the text. Okay, so sine is equal to -3 over 5. Okay, and cosine is 4 over 5. As long as you have those two, you can calculate the rest. So here's the sine, here's the cosine. The rest, all you have to do, use the relationship that they have with sine and cosine, okay? Instead of using, for example, tan theta equals y over x, you can even say tan theta is equal to sine over cosine. So whichever is easier for you. I'm going to get section 6.3, properties of trig functions. And so in this section, we're going to look at the domain and range and period of trig functions, determine the signs using the quadrant that was discussed last time, and fundamental identities. So the very first thing, what we covered in the previous 2 sections are here, okay? In the last one, the main idea consists of 2 things. Whether we deal with a unit circle, which is x squared plus y squared equals 1, or x squared plus y squared equals r squared, we should recognize how to calculate trigonometric functions. The most important thing to remember, x corresponds to cosine, y corresponds to sine, and that will help us figure out whether in a specific quadrant, whether a sine or cosine is positive or otherwise. So in this section, and there were some common arcs that hopefully we are very comfortable with. In this section class, the very first thing is about the domain and range. We will discuss that with more details in the next section when we do the graphing, but for now, the domain and range, as far as the sine and cosine is concerned, is all real numbers, the domain. But the range is limited to -1 to 1. For tangent and cotangent, we also have limitations as far as their domain, the rest of them, as far as the domain is concerned. As far as the range, tangent and cotangent are all real numbers. So we'll see that as we look at the graphs. The next page also is fairly basic, and that is determining the period of a trig functions. Okay. 2 pi is called the period. And Let's just put this in slide mode. And so what that means is the functional value of a function, when it's a periodic function, it repeats itself after a period is passed or multiples of that. So for example, in the case of a sine or cosine, the period is 2 pi. So therefore, if we multiply the 2 pi by any integer, that's why we use 2 pi k. Sometimes we use 2 pi n, depending on the text. The functional value makes no difference. It's the same thing. In the case of a tangent and cotangent, it's no longer pi. It is no longer 2 pi. It's only pi. I want you to know that. In fact, when you go to the third quadrant and look at the values of tangent and cotangent, both of them are positive. Okay, so that's important to remember. All right. Again, these are basic stuff, I hope, that we remember from basic trigonometry, functions that we have learned in trigonometry. So let's look at a couple of simple examples, starting with example 1. We are interested in finding sine of 17 pi over 4 when the angle is larger than 2 pi. Or if you look at the negative side, it's beyond negative 2 pi. You can take off multiples of 2 pi. So I hope you see that 16 pi over 4 equals to 4 pi. So this is equal to 4 pi plus pi over 4. And that gives us the same as pi over 4. It's a common arc. We are supposed to know the answer. What about cosine 5 pi? Cosine 5 pi, we can take out again multiples of 2 pi. That means you can take out 2 pi or 4 pi and so on and so forth. 5 pi, we can take out 4 pi, and it gives us only pi. Cosine of pi, a common arc, is -1. In the case of a tangent, if you recall, the period is only pi. So if we take out the pi, it gives us pi over 4, and we should know the answer. Sounds good? Everybody is following that? So we are taking off multiples of the period. For sine and cosine is 2 pi. For tangent and cotangent is only pi. Okay. We are going to move on, class. Okay. Again, if anyone has a question or something happens that you need to let me know, please do not hesitate. Determine the signs of trigonometric functions in a quadrant. Well, we know x squared plus y squared is 1. X represents cosine, y represents sine. Okay. And tangent is y over x, so on and so forth. Okay, it's not a big deal. If we look at, so this is for the case that is shown here. If we look at what's given based on the quadrant, we can make a decision. Okay. So what I want you to see, and it's very simple. Okay. I'm going to show it on this one. S and C. Okay. Both of them are positive. So the first one represents S, the second one represents cosine. In the first quadrant, they are positive. In the second quadrant, sine is positive. Cosine is negative. Why is that? Because sine is the y-coordinate, cosine is the x-coordinate in the second quadrant. Cosine or x would become negative. In the third quadrant, both of them are negative. So sine is negative, cosine is negative. In the fourth quadrant, sine is negative and cosine is positive. Why is that? Because cosine is represented by x. As long as we remember this, we can figure out the rest of it. And just for the sake of argument, in the third quadrant, if sine and cosine are both negative, tangent must be negative over negative is positive. And from there, we can figure out the rest of it. Now, I hope you don't have to memorize this. As long as you remember what I drew for you in red for sine and cosine, and the reasoning, okay, is because of the pair, okay. Cosine is x, sine is y. You are pretty much done. Okay?
Yeah. I have a little trick to remember.
Yes, please. I appreciate. Please share with us.
So my trigonometric instructor told us this little trick. It's all students take calculus.
Okay.
So all for A,
All students take calculus. Okay, go ahead. Oh boy, I messed it up. Sorry. Go ahead.
Okay. So in the first quadrant, all of them are positive. Second quadrant, just the ones with S are positive. Well, in this case, sine. And then third quadrant will be tangent. And then the fourth quadrant will be cosine. So I don't know. That's how I remember.
That's, you know what, I really appreciate it. You know, any method that works for you, please stick with that. And I really appreciate it when you share it with class. Okay, we all learn. Okay, I love to hear it from the students. This is fantastic. This is good. If it helps, by all means. Okay, by all means. All students take calculus. That sounds good to me.
Yeah, one for each.
All right, thanks.
Basically.
Thank you so much. That sounds great. Okay, this is good. Are we ready to move on, class?
Yep.
Perfect.
Yeah.
So here's a simple example. We have a sine that is positive and cosine that is negative. All right. So which quadrant is that?
If sine's positive and cosine's negative, that's quadrant 2.
I mean, I honestly, the justification is here, but it's very straightforward, okay? If you want to go one by one and discuss it, you can do that. but since they come together in one shot, you should recognize this quadrant 2. If not, you can say sine is positive, it's at top, so it's either the first or the second quadrant. Cosine is negative accordingly on the left side, second or third, and you bring them together, and you make a decision. So however you come up to the decision, that's absolutely fine with me, okay? Now, these are the quotient identities, okay? And these are the reciprocal identities class. Everybody remembers them, I hope, okay? So this is the example we want to look at. Again, the identities that you see, we've seen them, you're comfortable with those. And so we're going to use them to evaluate this. So what I'm going to do, I'm going to give everybody a moment, about a minute, see if you can figure out where sine is given and cosine is given, all right? And we want to figure out the rest of them. So let's give everybody a minute, see if you can come up with the answer. All right, the way I would do that, class, I would do tangent, which is sine over cosine. And then just the reciprocals of those three is the rest of it. So sine over cosine, which is 1/3. Okay. Why is that? Because this is a complex fraction. Those things cancel each other. So you have square root of 10 over 3 square root of 10. Let me use a different color. Okay. Square root of 10 cancels square root of 10, you end up with 1/3. It's that simple. Now, because this is 1/3, tangent is the cotangent is the reciprocal, which is 3 over 1, or simply 3. Cosecant is 1 over sine theta, 10 over square root of 10, and it becomes square root of 10, and cosine theta, flip it over, and 10 over 3 square root of 10, and you have all of this. Do you have to take all those steps? I hope not. So if I'm doing this, as long as I'm given sine and cosine, I quickly copy tangent, and the rest of them are simply reciprocals class, reciprocals, okay? And it shouldn't be a big deal. So rationalization is normally a good idea, and that's what we do. Sounds good? So we use quotient identities, reciprocal identities to get there. I believe we're ready for the next slide. All right. So here's a very important identity. So we know x squared plus y squared equals 1, right, class?
Yes.
And we know x is represented by cosine, y is represented by sine. So cosine squared plus sine squared, or sine squared plus cosine squared is 1. This is one of those Pythagorean identities, okay? Here's the name, class. This is one of them. Now, what about the rest of them? It's very simple. Let's divide both sides, once by sine squared, figure out what we get, and once by cosine squared to see what happens. So if we divide by cosine squared, class, can anybody tell me what we get when we divide both sides by cosine squared? What is sine squared over cosine squared?
It'd be tangent squared.
That's it. Tan squared, okay?
Plus
You're
1.
dividing both sides by cosine squared, so tan squared plus 1, and the right side?
Secant squared.
Secant squared. Now, what if we divide both sides by sine squared? What do we get, class? So this original one, now divide by sine squared. What do you get?
Cotangent squared.
1 plus cotangent squared equals cosecant squared. You can put any of them first, it doesn't matter. So these three are known as Pythagorean identities. Pythagorean identities. So far, Pythagorean identities and some, reciprocal identities, put them together. Those are known as fundamental identities. I hope we are comfortable with those. I hope we remember most of them from trigonometry, so we can move on. Okay.
Yeah.
Yeah.
Perfect. All right. Let's see what happens here. We're going to find the exact value. And so we start with the first one. And we're going to rewrite 1 over cosecant squared. Generally speaking, when we begin working on things, we try to write them in terms of sine and cosine, unless there is a better way, and we will look at it when there is a better way. So in this case, part A, 1 over cosecant squared, what is that equal to? What can we replace it with? Anyone? 1 over cosecant squared. See, I'm not even mentioning 35 degrees. That's not important to me. So 1 over cosecant squared, we can replace it with? I can't hear you.
Square.
Say it again, please.
Sine square.
Sine squared. And sine squared plus cosine squared equals? 1.
Equals 1.
1.
And you're done. I hope you see how easily we can handle this. Okay. That sounds good? Everybody?
Yes.
Yes.
What about part B? What would be the fastest and easiest way to handle it? Any ideas?
Well, you could either convert cosine over sine to cotangent. Yeah, you could do that.
Very good. And so what do you notice? What's the answer? Final answer is they're identical, 0, right?
Yeah.
Yeah.
Okay, so that's done. That works? Simple? Everyone?
Yes.
Okay. How about this one?
Tangent 20 minus tangent 20.
Oh, I meant to bring this one up, which is 0. Very good. Very good. What about the last one?
Sine squared pi over 12 plus cosine pi over 12.
Cosine squared.
Cosine squared pi over 12 equals 1.
That's it. Very straightforward. Done. Not a big deal. So knowing the identities would be nice and helpful. Okay, we need to be very comfortable with those. Okay, class? All right. Okay. Move on. You want to look at more examples, class? To find trigonometric functions, class, we can go by using circles of radius r by drawing a circle centered at the origin, And remember, x squared plus y squared is r squared. So for figuring out x and y and r will do the job, okay? And the other method is just using the identities, okay? And you can ignore that. Just, you have seen how we go through those definitions that we have seen. For example, cosine is x over r. Sine is y over r. That's all you really need to remember. The rest can be found through sine and cosine. Okay, so here's the method. We want to find the situation, and there are two methods. We're going to use both methods. In fact, I would mix and match. That's fine with me. The very first thing is to locate the quadrant, okay? So we can figure things out. We know sine is 2 over 5, which is positive. Cosine is negative. That gives us what? Which quadrant, class?
Four.
Quadrant.
Quadrant?
4.
What the hell? Number?
Cuatro.
Quattro is wrong.
Quadrant 2.
Okay, that's as much Spanish as I know. Number 2, if sine is, notice class, when sine is positive is above the x-axis. So above the x-axis. Why is that? Sine is the y coordinate, class. Cosine is negative, is to the left of the y-axis, and that gives you the quadrant. Okay. If sine is 2 over 5, okay, that means y over r is 2 over 5, and we need to find the missing x. Okay. So you go through the process and you find x to be plus minus square root of 21. Which one are you going to use? Minus square root of 21, right? Because
Yes,
this is what I
that's
mean by
negative.
understanding the quadrant and what happens in each quadrant, okay? X is negative. You're in the second quadrant. Now you're practically done. Cosine is x over r. As long as we have cosine, we have the rest of it. We have sine, we have cosine, we have the rest of it. So here's cosine. What is tangent? You can say sine over cosine or y over x. That's your choice. Either way is fine. What about the other three? Just flip them over. Because I'm being, I'm using in essence some of those fundamental identities. Or I can say cosecant is r over y. I wouldn't bother with that. Just flip them over and you have the rest of it. I do give you the formulas, r over y, r over x. And so again, here's for example, sine, right? Sine is y over r, okay? So that means cosecant must be r over y. So just go with the reciprocal, that's just as good. Is everybody following that? Finding out the quadrant and therefore figuring out the sine is the most important piece. If you don't have that right, everything will be wrong. Okay, class? Everybody?
Yeah, sounds good.
Very quickly look at the same question. I don't want to spend too much time on it, but the method of identities, generally speaking, any method is fine. Okay, ultimately, when you move on to the next, what is going to be what method? Here's the question, what's the answer? Use any method, and normally we should be very comfortable with identities. Okay, class? We should be very comfortable with identities. All right, so let's go to the next page and look at the same question. And by the way, everybody's done here, right?
Yes.
Yes.
So we're going to look at the same question. And we're going to use the identity. Since sine is given, we need to find cosine because sine squared plus cosine squared is 1. And that's a simple identity everybody remembers, is known as one of those Pythagorean identities. So you put it in, and cosine can be found having two answers. Okay, now you make a decision. Which one? We've already discussed that. In the beginning, right at the top, it says cosine is negative. So you choose the negative one. Okay, theta is in quadrant 2, and cosine is. The rest, you just follow, you go through the process again. Tangent is sine over cosine. And the other three are the reciprocals, class. I'm going to give everybody a moment to put their thoughts so we can move on. All right, sounds good. Is everybody okay with that? Now, I hope that I'm really mostly interested in quickly recognizing the quadrant calculation. I don't find it difficult. You do find it difficult either. Okay? Sounds good. Ready for the next one, class?
Yeah.
All right. Here's the next one. Cotangent theta is given, and we know sine is negative. So I want you to think about this, see if you can quickly figure out the quadrant. As long as we have the quadrant, the rest goes fairly nice and easy. So, what is the quadrant?
Quadrant 4.
Quadrant 4. Let's discuss that. Cotangent is positive. So cotangent is positive in two quadrants. What are those quadrants?
First quadrant and
One
fourth quadrant.
and, say it again?
The first and fourth quadrants.
No, that's wrong.
First and
Cotangent
third.
is the same as tangent. Both
First
of them
and
are positive in the first
Oh.
and third quadrant. First and third quadrant.
I misread that. I thought that was cosine. It was cotangent.
Oh, okay.
I'm sorry.
Okay. Oh, yes. Cosine is
first and
positive
third.
in the first and fourth quadrant.
Yeah.
Cotangent in the first and third. Sine is negative. In which quadrant? Sine is negative.
The third and the fourth.
Therefore, the answer must be
Quadrant 3.
beautiful, beautiful, beautiful.
Oh man, this takes me back.
Sounds good, everybody?
Yeah.
So cotangent is 1/3. And so here's the graph. In the third quadrant, x is negative, y is negative. Cotangent is 1/3. And cotangent is x over y. We can figure out the r, which is square root of 10. So we have x, we have y, we have r. We just have just about everything. So obviously the first easy one would be tangent, which is 3 over 1, or simply 3. That one is out of the picture. Cosine is x over r, and sine is y over r, and the rest are reciprocals. Tangent, that would be a quick one. Cosine, x over r. Cosecant is 1 over that, is the reciprocal of that. Cosecant actually is 1 over sine. Okay, 1 over sine. The order, I'm not too crazy about the order. Sine is y over r. The order is not the way I wanted it, class. Okay, so in any event, I hope everybody is clear. The order wasn't, it should be, but finding the answers shouldn't be a big deal. I think we are ready to move on. If there are any questions, again, the order wasn't right. But the concept is straightforward, I would say. All right. If you want to use identities, cotangent is 1/5, sine is less than 0. Anything comes to mind? We had 3 Pythagorean identities. Remember what we need. We need to have at least one more, and we can figure out the rest nice and easy. We've already come up with the quadrant. Okay, we justified it, and the quadrant is 3. We already know that. Okay, so we therefore know the sign of everything. Obviously, from cotangent, everybody can get to tangent. It's not a big deal. In no time is 5 over 1. 3 over 1, my apologies. Okay, I mentioned this is, okay. And it's not a big deal. But, what Pythagorean identity am I referring to? Anybody? Cotangent square plus 1 equals cosecant square. Okay. We can easily get to the rest of them going through that process. I will mention a different method in a moment, but for now, tangent is easy, is the reciprocal. We can find the rest of them by finding, using this identity. Cosecant becomes plus minus 10 over 9, or plus minus square root of 10 over 3. And we use the negative. The reason why we said it's the third quadrant. In the third quadrant, everything is negative except tangent and cotangent. Now we are practically done. Okay, if this is cosecant, sine is the reciprocal of that, tangent is the reciprocal of a cotangent. Okay, so those are easy. Now we can use this formula. Cosine is sine over tangent. Let me make sure everybody understands how we arrive at it. You can say tan theta is a sine theta over cosine theta, right, class? So therefore, cosine theta is sine theta over tan theta. This is the fastest way to get that. And secant is just the reciprocal. Make sense? Everybody okay with that, class?
Yes.
Again, if you have different identities in mind, it's not a problem at all, okay? It's absolutely up to you. But from cotangent, we can only get to tangent easily. But we have to get something else to get there, okay? So from cotangent, the reciprocal is the tangent, but what about the others? You have to use Pythagorean identity. All right. We got to go to the next question, everybody. Everybody is fine with this?
Yes.
I hope you realize that, the weekend is coming up. You got to practice with the identities, because when we go to equations and proofs, you really need to be very comfortable with this. All right. There's something called using even and odd properties, okay, to find the exact values of trigs. Anytime you have trigonometric functions of a negative arc or angle, you must get rid of that and make the angle positive. However, you have to realize what's the result. And the result is every trigonometric function is an odd function, except cosine, because cosine is even, so is its reciprocal secant. Okay, cosine is even. And so I want you to see why. For example, if we say cosine of pi over 6 or negative pi over 6, it's the same. The reason why, because cosine corresponds to the x coordinate, everybody. Okay, so whether you go clockwise or counterclockwise, you are in the first or fourth quadrant in the case of a pi over 6 as an example. Okay, so that's important to recognize. So if you look at this graph, of course, theta and negative theta, you're looking at the reflection with respect to the x-axis. X doesn't change, therefore cosine doesn't change. If cosine doesn't change, secant doesn't change. Okay, and we're done. So now, quickly, cosine of negative 60 is the same as cosine of 60, and it's 1/2. Okay, class? Now, what about sine of negative 390? I want to spend a few minutes on the next section. So, all right, the first thing we want to get rid of the negative. And we know sine is odd, so it comes out. That's the first thing. Now, 390 is larger than 2 pi or 360 degrees. By how much? By 30 degrees. $390 is 30 plus 360.
Professor, question.
Go ahead.
I'm sorry to stop you here, but I'm just a little confused between the last
I'm very sorry, but I have a hard time hearing you. A little bit louder, please.
Okay. Can you hear me better?
Yes.
Okay. Sorry to stop you, but I just had a question. I was confused why in the first example, when you have negative 60 degrees,
Yes.
it's positive cos 60 versus in this example, the negative goes in front of the sign.
Okay, look at the top, even and odd properties. Cosine is an even function. Okay, cosine sine. That's what. Do you see that? Sine of negative theta is negative sine theta. Does that make sense?
For a second, I thought maybe it has something to do with where it falls on the quadrant, but okay, I understand. Thank you.
That's not, so it makes sense, right?
Yes.
Perfect. So we have negative sine of 30 plus 360, or negative sine of 30, and that one is negative 1/2. Okay, now, what about tangent? Again, when the argument is negative, you have to take it out. In the case of trigonometric functions, all of them are odd except cosine. With cosine goes secant because secant is 1 over cosine, okay? So negative comes out, so you have minus tangent, okay, of 37 pi over 4. That sounds good? Now, we have to take out multiples of 2 pi, and we recognize in the case of the tangent, we don't even need multiples of 2 pi. All we need is multiples of pi, okay? And so 36 pi over 4, which corresponds to 9 pi, can come out. So this is the same as negative tan pi over 4, which is negative 1. Sounds good, everybody? Any questions?
No, I got it.
Perfect. So we're going to go to the last question, class.
Okay.
All right. Now, let's just, this is 2 pi, class, not 2. Okay, 2 pi. Can you simplify this and come up with the answer? Can anybody see the answer here?
3 cotangent theta.
Very good. Each one is cotangent theta. So again, cotangent theta plus cotangent of theta minus pi and cotangent of theta minus 2 pi. Because the period for cotangent, okay, is pi, whether you add pi or multiples of pi, or subtract pi or multiples of 2 pi, makes no difference. There are 3 of them, and that's 3 times negative 2 equals negative 6. We're going to get the last question, and then we want to spend a few minutes on the next section. Here's the question that is interesting, okay? So you're looking at sine of 1, sine of 2, and so forth. So what happens is there are a bunch of them that are positive. So we start from the last one and see how we can replace that with. Everybody can see, for example, this one, sine of 59 degrees. It's 1 degree less than sine of 360 degrees. Everybody can see that, right? And it's the same as sine of negative 1 degree. So we're going to rewrite it in this fashion. Is everybody with me so far?
Yeah.
Okay. Now, sine is an odd function, which means, for example, this one is minus sine of 1 degree. This one is minus sine of 2 degrees, and so forth. So understand what's going to happen. So I want to make sure everybody understands what we end up with. On the positive side, we are going to go, I want to show that to you. On the positive side, okay, so let's rewrite this now, of course, in this fashion. On the positive side, we're going to start from 1 to 3 and we're going to go all the way to 179. So let me write those two. I want to write a few in between because I want to make a point. So sine of 1, sine of 2, sine of 3, sine of 4, all the way to sine of 179 degrees plus sine of 180 degrees plus sine of 181 degrees. And of course, the rest of it. Now, why am I writing the middle ones? Because I want to make a point. The point being, let me use a different color. The point being, what happened? Very good. No. Yeah, that's fine. The point being, sine of, okay, I'm not making this happen. Sine of 179 and sine of 181. Sine of 181 is the same as minus sine of 179. Okay. And as you should be able to see from the get-go, it's like sine of -1. So everything cancels out, but the sine of 180 remains. Sine of 180 remains. However, sine of 180 is 0. Okay, class?
Mhm.
Yes.
All right. I want to spend some time on the next section. It shouldn't be too long, but it's worth, doing something there. And so I'm going to go to the next section. Is there any question? Is everybody okay with this? Are we ready to rock and roll?
Yeah, okay.
Perfect. All right, so everybody is looking at section 6.4. Want to look at the graphs of some functions, in this case, sine and cosine, okay, different sinusoidal functions, okay. We looked at section 1 and 2 and all these identities, okay. We really have to be comfortable with those so we can move on. I put the synopsis of those pages, those sections. So, for example, the one we just covered, we have some fundamental identities, okay, that consist of Pythagorean identities, reciprocal identities, okay. We have even and odd identities. We have also periodic, functions, and the period is 2 pi for all of them except tangent and cotangent, okay. This is, of course, cotangent theta class. So, anyway, that's one of those things that sometimes, in any case, that is supposed to be, let me just do this. Let me put it in slide mode. This is cotangent theta. All right, so that's very straightforward and everything that we have seen before. Let's go to the graph. So I want to start with the graph of the function y equals sine theta. Okay. Now, in the beginning, sine x or sine theta. In the beginning, when we don't know anything about a function, we just plot points, as you know. Okay. So we just have seen the value of trigonometric functions for common arcs, so we can use those. Okay. So for example, if we put 0 to pi over 2, a bunch of numbers, for example, pi over 6, pi over 4, pi over 3, and pi over 2. That would be for the first quadrant, we have a bunch of numbers. In the second quadrant, from pi over 2 to pi, we can pick something in between. We don't have to pick all of them. We can pick 5 pi over 6 or 2 pi over 3, or you name it. And now you're going to evaluate the sign x. I hope you remember all of those. So that would be the second column. Everything comes from the previous section. All of them are common arcs. Those are the pairs. Okay? Those are the pairs. Now, if you plot those pairs carefully, and this is, posted completely. So this would be the graph for one complete cycle. Needless to say, this thing continues indefinitely on both sides, class, and I can't really emphasize this enough, okay? But for now, when we look at this graph just the way it is, we notice that the range has a limitation. The range goes from -1 to 1. Now this one, we are showing just from 0 to 2 pi. However, there is no limitation as far as the domain goes. You can continue indefinitely on both sides. Now, this is for x being between 0 and 2 pi. Now, here's one easy way to graph any sinusoidal function, whether it's sine or cosine makes no difference. The process is very simple. You come up with the key points for 4 arcs. Okay, I want to make sure everybody understands what we mean by those arcs. So take a look at this one. From 0 to 2 pi, we cut it into 4 equal pieces. We cut it into 4 equal pieces. This is one arc. Okay, let me show you the second one here by single different color. Here's the second arc. So 0 to pi over 2. Here's the second arc. Okay, from pi over 2 to pi. The third one from pi to 3 pi over 2, and the last one from 3 pi over 2 to 2 pi. Now, does it have to be 2 pi to cut it into 4? No, the period normally is 2 pi, but it's not the case if you have a different function of x. For example, sine of, I don't know, 10x, then things are different. But what we do, one easy way, cut it into 4 arcs and just graph each one and you're done. It's that simple, class, okay? Now, notice, so we have this completely posted. Notice when we want to graph y equals sine x, it's really not restricted from, let's go back, from 0 to 2 pi. It goes indefinitely on both sides. What I'm interested in is that normally you graph one complete cycle and show all the details, and then if you have to move on to both sides, okay, indefinitely. Sometimes just one cycle is good enough because the assumption is everybody knows it's periodic and everybody can handle it. I want to quickly show you the cosine, okay? Again, it's just a matter of using a proper common arcs. So we want to graph the cosine. Can I assume everybody is okay with this, class?
Yeah.
So here's the cosine. We do the same thing. We pick up a bunch of x coordinates. The y is cosine x as an example. Cosine 0 is 1. Cosine pi over 3 is 1/2. Cosine pi over 2 is 0. And the rest of them follows. Just for the sake of argument, notice cosine of 2 pi over 3, class. You use pi over 3 and then you pay attention to the sign. So it's, the value is the same as 1/2, but the sign in the second quadrant cosine is negative. And that's up to you to remember that. So those are the pairs. And here's the graph. Okay. So sine starts from 0, 0, but cosine starts with 0, 1. Okay. From 0 to pi, it's decreasing, and then from pi to 2 pi is increasing. Whereas in the case of a sine, 0 to pi over 2 is increasing, pi over 2 to 3 pi over 2 is decreasing, and then 3 pi over 2 to 2 pi is increasing. Now, we're going to cut this in 4 pieces. And we make up 4 arcs. So take a look at these 4 arcs, class. And take a look at important key points, 0, 1, the y-intercept, pi over 2, 0, and 3 pi over 2, 0. Those are x-intercepts. Pi negative 1, it's the minimum value of the function. 2 pi 1, both of them, 0, 1, 2 pi 1, both of them represent the location for the maximum. Now this is only one cycle, class. Okay. This is the general form. Does that make sense? Is everybody okay with that?
Yeah.
Yeah.
If you don't mind, I just want to do one example, and that's it for tonight. It won't take long. And at the very least, we get this concept started. So you need to know the general shape of a sine and cosine. Okay. So let's take a look at the next page. A sine omega x, graphing this function, class. A is called the amplitude, okay, which is normally 1, okay? So I want to make sure everybody understands what I'm referring to. Never mind the question. When y is sine x, period is 2 pi, amplitude is 1. But if we change it to y equals a sine omega x, what happens? Everything changes. Okay? Your period is 2 pi divided by omega now. 2 pi, you have to divide the 2 pi by the coefficient of x. What about the amplitude? The absolute value of the number sitting in front of sine. Okay? So here's y equals sine x. You know the basics, and again, as far as I'm concerned, one cycle is good enough. Okay. So 0, 0, pi over 2, 1, 3 pi over 2, negative 1, 2 pi. Those are, I mean, just one cycle is good enough. So if you look at just one cycle, you're looking at, okay, those important parts. So if you're looking at only that part, so what happens is that the period stays the same, okay? What changes is the amplitude is now number 3. Do you see that, everybody? So if you want to go with the transformation, there's a vertical stretch. And that's understood, which means your domain is not changing. It's all real numbers. Okay? It is the range. which was -1 to 1 here. Range was -1 to 1 here, okay? It is no longer the case here.
It's really interesting
Sounds,
seeing that class because I'm seeing it in my electrical class similarly with amplitude.
I'm so sorry, I couldn't hear you. One more time, please.
I said it's interesting seeing this in the math class because I'm doing
Yeah,
something.
yeah, but the thing is, in electronics and in electrical engineering, you only deal, mainly deal with sinusoidal functions. Yes, absolutely. It comes from here. You learn this, you have an easy time there. Sounds good, everybody?
Yeah, sounds good.
Yeah.